Hello Kidlets, this is your second video. This is taking a look at magnetism and energy within the sun and the effects that we see, such as sunspots. So sunspots are actually cooler regions of the sun. They are the darkened areas we can see here. They can be 2 to 3 times the size of Earth for comparison. They're surrounding by some filaments here, and we can see that the spot itself is much darker than the surrounding area. The filaments are actually hotter. So even though sunspots are associated with warmer temperatures on Earth, they themselves are cooler. These form at specific latitudinal bands, so about 30 degrees. So if we were to take a look at comparatively the Earth, there's about the equator. 30 degrees would be about where we are, so it's like mid-latitudes. And these migrate. They can last for days or months, and they often appear in pairs or groups, and they can fragment and split throughout their life cycle. So here is an image of a sunspot with a flare erupting from it. And the reason that we have spots at all is because the sun is like one giant bar magnet. We have polar north, we have polar south, and the poles are these areas of magnetic intersection. So we can see that the magnetic field lines connect the poles, but we have intense magnetic energy happening between them. So just like a bar magnet has this wrapping of their field lines, the sun is the same way. So the sunspot cycle is directly related to the magnetism within the sun. And the sun, being a ball of rotating spherical gas, not rock like the Earth, has something called differential rotation. And what that means is that the equator rotates faster than the poles. And as we'll see in just a second, the measurable day on the sun is different depending on where you are. So because the sun has differential rotation, throughout its rotational cycle, it causes the path of these spots to change, and it causes them to stretch. And we think that these spots are formed specifically over areas that either have increased magnetism or areas of magnetic anomaly. But the magnetism within the sun is really complex. And the study of the magnetism within the sun is called helioseismology. So seismology associated with movement or earthquakes. And that's actually what's studied, is how much movement the surface of the sun has associated with that convection within the convection zone. So differential rotation has a consequence of different portions of the sun rotating at different ways. So we can see at the equator that rotation is about 25 days, nearly 3 days longer if you were at the poles. And the sunspot cycle we think is approximately 11 years. So for a full cycle would be 22. So 11 years to complete one, but to get back to normal is 22. And the reason is that the magnetism within the sun is so complex and complicated that after it completes one cycle and through the end of this 11-year cycle, the sunspots become so intertwined with the magnetic field, and the magnetic field lines become so twisted and complex that the poles switch. So we have a polar reversal every 11 years. So that full cycle takes 22 years to get back to magnetic normal. So here we can see some pairings, some groupings of sunspots. So we can see the latitudinal bands that they specifically format. If rotation is going this direction. So we can see the leading spot here. So the way this happens is you have spots that form and they fragment and break up. And one spot goes towards the equator, the other spot goes towards the poles, because these have different polarities. So each would migrate towards a different pole. So we can see how far along that particular cycle of spots are, because each of these spots only last, say, a month or so. So you can track the life cycle of a spot by how broken up it is, how many fragments you have, and how far apart they've split. So when they form, it just looks like one, but they split apart throughout their life cycle. Here are some videos we will look at. And if we were to track that cycle, knowing that it's approximately 11 years or so, we can actually link that to climate on Earth. And this was started over 100 years ago. So we can track areas of sunspots to climatic events on Earth. So we can see maximum number of sunspots, minimum number, maxima, minima, maximum, minima. And we can track that to climate. Now remember that sunspots are actually cooler regions of the sun. Yet if we were to link that with Earth's climate, we can see the areas where we have maximum sunspot, we have warmer winters. And minima, so down here where we have a minima, we have much cooler, which is kind of crazy. Think about that one. So we have areas of cooler regions on the sun, warmer Earth. And that was really a mystery for a long time, but what scientists have figured out is, if you remember back in that first picture I showed you the filaments surrounding the sunspots, the filaments are significantly warmer than the average photospheric temperature. So because of that, that warms the general energy coming from the sun. So that means that just because of those filaments can be just as big, if not bigger, than the sunspot itself. So having an increased area of filament actually increases the average surface energy of the sun. And that's why it's associated with warmer. So we have higher energy, possibly into the UV even. And that's why it's associated with that. So we can see that sunspots have been tracked for a really long time. It does not take a high degree of technology or proficiency to be able to track these. My astronomy club is actually tracking these. So we have an area here called the Maunder Minimum, and this is an area where we had a very large famine spread across Europe, lots of starvation, nothing grew because it was significantly colder. And then we have some warmer years here. We had a heat wave in London and Paris, and we can see that, I mean, there are natural progressions of the solar cycle associated with climatic events. That is not currently what we are in. We are actually currently in a solar minima. So if we were to track that, and remember that this is a map of the sun. I know this can be a little confusing. It does look like a butterfly, but here is the latitude. So equator is at the middle. So this is tracking the progression of spots from year to year to year. And if it were plotted over time, it actually looks like a butterfly because those spots fragment and move away from the equator and towards the poles. So that would be what it would look like. And very rarely do you actually see it getting above. But as we have an increase in technology, we're able to track these to a more finite detail, which was much harder back here. So that's probably why you have the lack, not because the spots didn't exist, but just because people couldn't detect them. So as I said before, we have the rotation of the sun, which is pulling apart the sunspots. Those sunspots are directly tied to the magnetism of the internal surface of the sun. So the more sunspots you have over time, that begins to distort the magnetic field lines within the sun. So after 11 years, it becomes so complex that it rearranges the entire magnetic cycle of the sun. It flips the polarity and starts again. So here's a couple practice questions for you. This is looking at Stefan Boltzmann's law. We looked at this last semester. So looking at your temperature to the fourth power yields the amount of energy you have. So your sigma is actually a constant. If you cared to actually solve this problem, you could look that up, but it's a constant of proportionality. So moving on to the corona and the chromosphere, we can see that the corona is where we detect this high energy solar wind, which we can think about not as like a wind, but as a constant stream of flowing high energy plasma and particles from the sun. So this is extremely high velocity, and this causes the sun to constantly lose mass. So all stars are constantly losing mass, but this is balanced by the fact that there is energy production in the core. So that's why the star stays constant and stays stable when it is in this phase of stellar evolution. As we will see, our star is a main sequence star. It'll be stable for about 5 to 10 billion more years. Our sun is not getting any hotter. It is not getting any cooler. It is going to stay exactly the way it is for a long time. And we can see this because this is in X-ray. So we can see this area of energy coming out, and we can also see that associated with some activity on the surface. So we think that the solar wind is related somehow to these solar flares, so it's also somehow a consequence of the magnetism within the sun. So because the sun is magnetic, we could think about the sun's weather or space weather also being magnetic. So we can have storms on the sun that are much larger than Earth that can last for weeks. They can cause these huge eruptions and solar flares. They can disrupt communication satellites. This can affect the entire power grid. And if you think about the electricity you draw from your house, assuming you don't have solar power, which is actually still tied to the electric grid, you're drawing this from a power source that is run by a region or a city. So for us, we're drawing this from LA. Well, every city is supposed to have a backup generator in the event of a massive power outage. There's supposed to be over 50 in the US, and we actually have 2. So if there were a large event, a large solar event, it could wipe out all communications. And think about that. You wouldn't be able to freeze your food with no electricity, with no power. Your fridge wouldn't work. Gas stations wouldn't work. So unless you could hunt your own food and somehow store it somewhere, you'd be kind of done. So the sun could greatly influence events on Earth. And the largest known event is called the Carrington-Hudgens event that happened in 1859. Coincidentally, the very first solar flare ever observed was the largest. And if that were to happen today, that would wipe out the entire global power grid, wipe out every satellite in the sky, and we are entirely dependent on that space-based technology. When this happened, this caused intense auroras around the equator. People in the Caribbean noted seeing that. And I'll talk about this a bit more in class, but this was the era of the telegraph, and this burst transformers, and there were people that were able to unplug their telegraph lines and still communicate for about 100 miles because it was entirely powered by energy from the sun. So, and they have this all documented. It is pretty cool to read about. So this image is a tiny bit blurry here, I apologize, but here we can see this large solar event. We can see this influx of photons. Over here is the Earth, and we can see that all of these blue lines, that is our magnetic field that is protecting us from the magnetism of the sun. So we have Earth right here, this little teeny blob, and we have our magnetic field lines, our Van Allen belts, that are protecting us from those incoming solar rays. So in the event of a large solar eruption, what ends up happening is our magnetic field basically gets warped like this, and it extends all of the solar particles this direction. And those solar particles can interact with our magnetic field, and that is what gives us auroras. That's proof that we have a magnetic field, that we have this protection from the sun. So here we can see from space what that aurora would look like, because the poles are the intersection of our magnetic field lines. So as we have this incoming solar energy, this influx of solar wind particles, they interact and intertwine with our Van Allen belts, our radiation, our magnetic fields, and we see these dancing consequence of auroras. So what the auroras are, and the reason they're usually green, is it's ionizing atomic oxygen, and the line is actually the magnetic field line that you're seeing as you have electrons then essentially spiraling around these magnetic field lines. So it's that energy release, and that's why they move. So here we can see a prominence. It may not look like it's looping back, but it is actually looping back here, as opposed to a flare. So here is that prominence I showed you at the very beginning that's looping back. Here would be a flare, which is an eruption, and these are eruptions from the spots themselves. Here we can see that granulation. We can see the dark and light spots. So one of the questions that I would expect you to be able to answer is, how does solar activity affect us on Earth? And there would be many, many different ways you could talk about that, not just in terms of the effects of solar flares, but you could also talk about the good effects of having a sun. I mean, without it, there would be no us. And it took about 3 billion years for the sun to actually get to the brightness it is and give us a blue sky. We had an orangish red sky for the first 3 billion years of Earth's history until it got to its current luminosity and size. So the very last section is super important, but if you wanted to pause here and come back to it, feel free. Fusion is the energy source that happens within all stars, and this is what provides the energy for it to actually become a star as opposed to a nebula or a protostar. So the definition of a star is having high enough temperature and density to complete fusion, which requires 1,000,000 degrees Kelvin. And the reason that is because fusion is combining together hydrogen atoms. Well, hydrogen atoms naturally repel. They do not attract each other. So you have to have a high enough energy, high enough density to make them combine. And in the sun and all low mass stars, you have something called a proton-to-proton chain. So we have 4 hydrogen that combine together to get a helium, and you have this excess of energy. And that's what we see. That's that radiation is released in the form of gamma rays and neutrinos. So we end up with this helium atom. So in our star, you have all of these hydrogen atoms that are combining together to get helium. So the composition internally of the sun is constantly changing as it's transforming hydrogen to helium and releasing energy as the byproduct. So that process of combining like elements is called overcoming the Coulomb barrier, and that requires incredible amounts of heat and density and energy to be able to combine like things. So here we can see another image of that. So we get those hydrogen atoms that combine together to get a helium, releasing a neutrino and an energy as an outcome. So here's what that would look like inside the sun. And this reaction is happening constantly within the core of our sun. So there are so many reactions, it's equivalent to, I'm going to try and get this right, 100 quadrillion trillion reactions per second. That is a lot of reactions going on. So you end up with a lot of hydrogen being converted to helium. Eventually, our core of our sun is going to be hydrogen deficient and predominantly helium, which will signal the next life cycle of our star and all stars. We'll see in the next couple units that fusion within larger mass stars is a bit different than in lower mass stars, but in all cases they become hydrogen deficient, and which signals the next stage, which would be the giant stage. So this would be one of the questions I would expect you to be able to answer. And that is it for you guys. I will see you in class. Have a wonderful day.